Heterocyclic compounds. Cyclic compounds containing one or more heteroatoms in the ring of carbon. The most common heterocycles are 5 or 6 member ring. For example, 5-member ring pyrrole, furan, thiophene, and 6-member ring pyridine. Here we can see the structure of the pyrrole, furan, thiophene, and pyridine. The molecular orbital structures of the pyrrole, furan, thiophene, and pyridines are these. Structure of the pyrrole contains 4 carbon atoms and 1 nitrogen atom in the ring, and this is the structure of pyrrole. All atoms in the ring are sp2 hybridized and lie in same plane. Contains 3 sp2 hybrid orbits in one unhybridized orbital containing 1 single electron on each atom. Out of 3 hybrid orbitals in an atom, 2 overlap with hybrid orbitals of adjacent carbon atoms to form 2 sigma bonds, and the remaining sp2 orbital overlap with s orbital of H atom to form another sigma bond. Unhybridized p orbitals on each C atom contains single electrons, whereas in nitrogen it contains 2 unshared electrons. These orbitals lie perpendicular to the plane of the ring and overlap laterally to form pi electron clouds above and below the ring. Hence, pyrrole has pentagonal planar structure containing 6 pi electrons. Structure of furan and thiophene. Furan has a flat pentagonal ring of sp2 hybridized carbon and oxygen atoms with cyclic pi electron cloud containing 6 pi electron, and this is the structure of furan. In oxygen atom, out of 3 hybrid orbitals, 2 have 1 electron and 1 has a pair of electrons. 2 sp2 orbitals form sigma bond with adjacent carbon atoms. 3 hybrid orbital containing unshared pair of electrons remains as such. Remaining unhybridized p orbital having 2 electrons from pi bond bilateral overlapping with p orbitals of carbon atom. The structure of thiophene is similar to that of furan. Aromatic nature of pyrrole, furan, and thiophene. They exhibit aromatic character because they are cyclic and planar. All the atoms in the ring are sp2 hybridized. There is pi electron cloud above and below the ring of carbon. They follow Huckel's rule for n plus 2 pi delocalized electrons, where n is equals to 1 for n plus 2 pi es is equals to 6 pi s. General methods of preparation of pyrrole, furan, and thiophene. Preparation of pyrrole by heating furan with ammonia and steam in the presence of ammonium trioxide. By the action of acetylene on formaldehyde to give butane 1,4-diol, which on heating with ammonia under pressure gives pyrrole. And this is the chemical reaction. Preparation of the thiophene, heating and butane with sulfur. 560 degrees C by heating sodium succinate with phosphorus trisulfide. Preparation of the furan by heating phosphorus and steam in presence of catalyst amine and zetan chromate. And this is the chemical reaction in structure. By dry distillation of the mucic acid followed by the decarboxylation of the product furic acid, and this is the chemical reaction and the mechanism also. Electrophilic substitution in pyrrole, furan, and the thiophene, and this is the electrophilic substitution reaction. occurs at alpha position but not at beta position. The attack depends on the stability of the intermediate carbonium ion form. The intermediate form during the attack at alpha position is more stable than form during the attack at beta position. Let us see the carbonium ions form when attack occurs at position 2 and 3. Greater the resonating structures, greater will be the stability. Therefore, substitution occurs at position 2. And these are the chemical reaction in which shows the electrophilic substitution reaction in pyrrole. Pyridine. Pyrrole in reduction in presence of NiPT gives pyridine, which is more basic than pyrrole. These are the chemical reaction involved in this process. In pyrrole, electron of an atom are not free. In pyrrole, electron of an atom are not free. They are involved in delocalized system, but in pyridine, electrons on an atom are free and are easily available for acids. Therefore, pyrrole is less basic than pyridine, but pyrrole is more acidic than pyridine. Pyrrole, after losing proton, gives pyrrole an ion which is resonance stabilized. Therefore, pyrrole can easily lose protons and acts as a stronger acid. These are the chemical reaction involved in this process. Pyridine, after loss of proton, gives pyridine an ion which is not resonance stabilized. Pyridine, and these are the chemical reactions involved in this process called pyridine. And structure of the pyridine is this. This is the general structure of the pyridine. It contains 5 carbons on 1 nitrogen atom arranged in hexagonal ring. The nitrogen and the carbon atoms in the ring are sp2 hybridized. The 2 sp2 orbitals of each atom overlap with sp2 orbitals of adjacent atoms on either side to form sigma bonds. Third sp2 orbital of each carbon atom overlap with s orbital of the hydrogen to give rise to sigma bonds, whereas third sp2 hybrid orbitals of the nitrogen presents the lone pair of electrons. The unhybridized p orbitals of each atom with a single electron lie perpendicular to the plane of the ring undergo side and overlap to form pi electron cloud above the and below the ring, as in case of benzene. Pi electron cloud contains 6 pi electrons which follow Haeckel's rule for n plus 2 pi electrons. Preparation of the pyridine by passing a mixture of acetylene and hydrogen cyanide through a red hot tube, and this is a structure with the preparation method which we can see. By heating pyrrole with the methylene dichloride in the presence of sodium methoxide, in which this is a chemical reaction involved in this process. By passing mixture of the acetylene, formaldehyde and ammonia over dehydration catalyst such as CuO and alumina, and this is a chemical reaction involved in this process. And the physical properties of these are colorless liquid having an unpleasant odor and soluble in water and many organic solvents. Chemical properties, a basic character. Electrophilic substitution in pyridine. Pyridine is less reactive than benzene towards electrophilic substitution reaction due to the greater electronegativity of the an atom. The pi electron cloud is displaced slightly toward the an atom, that makes ring slightly positive and deactivates the ring. However, it undergoes electrophilic substitution reaction under vigorous condition. The mechanism and the orientation of the electrophilic substitution reaction in pyridine is which we can learn. The substitution reaction preferentially occurs at position 3. It can be confirmed by comparing the resonance structure of carbonium ion formed during the attack at position 2, 3 and 4. Resonating structure. Out of resonating structures of intermediate structures 4 and 7 are particularly unstable because positive charge is carried by strongly electronegative an atom. Because of this, intermediate ion formed during the attack at position 4 or 2 is less stable than that formed during the attack at position 3. And this is the overall chemical reaction involved in this process. Nucleophilic substitution in pyridine. Pyridine undergoes nucleophilic substitution reaction more easily than benzene because of decreased electron density at ring carbon atoms. Substitution occurs preferably at 2 and 4 positions because the carbonium formed by the attack at these positions are more stable than that formed by the attack at position 3, and these are the entire chemical reactions. Carbonium formed by the attack at position 2 is resonance hybrid of the structure first, second and the third. Carbonium formed by the attack at position 3 and 4 are resonance hybrid of structure 4, 5 and 6 and 7, 8, 9. Structures 3 and 4 are particularly stable because negative charge is present on electronegative an atom. There is no such structure resulting from attack at position 3. This is the reason why nucleophilic substitution reaction takes place at position 2 and 4. Sichibina-Burnin reaction. Elimination of pyridine with sodium amide. Basic nature of pyridine. Basic nature: reacts with strong acid to form salts. Pyridine is more basic than pyrrole but less basic than alkyl amine. Two sp2 orbitals of the nitrogen overlap with sp2 orbitals of the carbon on either side. The unhybrid orbital unhybrid orbital pz forms pi electron cloud bilateral overlapping with pz orbitals of carbon. The sp2 orbital of nitrogen atom is unshared, containing 2 electrons, which are easily available for sharing with acids. In case of the pyrrole, the lone pair of electrons on an atom is involved in the delocalized system. These are not free for sharing with acids, hence pyridine is more basic than pyrrole. Role basicity of pyridine is due to the fact that the lone electron pair of the nitrogen atom lies in sp2 orbital, while in alkyl amine it lies in sp3 orbital. The sp2 orbital is smaller than sp3 orbital, therefore lone pair of electrons in pyridine is closer to an atom and is tightly held, hence less available for protonation in comparison to alkyl amines. Therefore less easily available for protonation. However, in pyridine, lone pair of electrons on and does not involve resonance and is easily available for protonation. Therefore pyridine is more basic. Reduction reaction of pyridine. Pyridine can be reduced more easily than benzene, thus reduced with hydrogen in presence of NaPT or with N-ethanol to give pyridine a million times more basic than pyridine. This is a chemical reaction involved in this process. In pyridine and in sp2 hybridize, where as in pyridine it is sp3 hybridized. Since the size of sp3 orbital is larger than that of the sp2 orbital, lone pair of electrons on Pyridine is tightly held with nitrogen, hence the electrons in sp3 orbitals of the pyridine are loosely held with nitrogen and are easily available for acids or electron deficient species.